Hi, I'm Sabrina, and today I'll be talking about phase changes of pure substances. More specifically, I'll explain the different components of phase change diagrams to help you understand how to interpret information from these diagrams. Before I begin, there are a few definitions that are important to know, like what is a pure substance? A pure substance is a substance that has a fixed chemical composition throughout. It's also important to know what a phase is. Everyone knows that solids, liquids, and gases are phases, but the more technical way of describing a phase of a pure substance is when it has a distinct molecular arrangement that is homogeneous and has easily identifiable boundaries. Therefore, the difference between phases is highly related to molecular bonds. So moving on, these phase diagrams that we will be seeing are related to three properties. There's temperature, pressure, and specific volume. Specific volume is not the same as volume, and it's defined as the volume of a substance divided by its mass. Okay, so now it's time to look at the diagrams. The first diagram that I will show you is temperature versus specific volume. So there's quite a few components to this diagram, so let me break it down a bit for you. Let's start with these 5 points on the dotted line. So along this line, we must assume that pressure is constant, as we see P1 is constant. So point 1 we have along this part of the line, as temperature increases, we have a compressed, also known as subcooled, liquid. This means it's not about to vaporize. Then as temperature increases, we reach this point, which is the intersection between the dotted line and the saturated liquid line. At point 2, we have a saturated liquid, which means it is about to vaporize. So we continue along at a constant temperature as specific volume increases to point 3, which can be anywhere along this line, and it is a saturated liquid vapor mixture. So then we get to this point here, the intersection between the saturated vapor line and the dotted line, where we get saturated vapor, which means it's about to condense. Then we continue where temperature increases along this line to 0.5, where it becomes a superheated vapor, which means it's not about to condense. So we can see that there's a second dotted line above that has a constant pressure that's greater than P1, as said there. So if we were to choose another constant pressure that's less than P1, then the line would be below it. This means that the location of each dotted line on this diagram not only depends on the saturation temperature, but also on the pressure. We will see this relation a bit later. So next, I'm going to talk a bit about quality. I'm not going to go into too much detail because I don't really have enough time, but I'll briefly explain how this relates to the different diagrams. So the quality of a saturated substance is the mass of saturated vapor divided by the total mass of the substance. This equation for quality is just based off the definition, and this equation tells us that the quality of a saturated liquid is 0 and the quality of a saturated vapor is 1. But if a substance is a saturated liquid vapor mixture, then it'll have a quality between 0 and 1. So here it's 0, here it increases, and it goes to 1. So next, I'm going to quickly show you the saturated pressure versus saturated temperature diagram. Basically just shows the relation between pressure and temperature that I was referring to earlier. So on this side of the diagram here is liquid, then you move to here, it's vapor. Pretty simple. Next we have the pressure versus specific volume diagram. It's very similar to the temperature versus specific volume diagram, but the main difference is that pressure decreases with respect to specific volume, while in the other diagram, temperature increased with respect to specific volume. But these two diagrams have the same components, so I'm not going to explain it again. I'll move on. So this is just an extended version of the pressure versus specific volume diagram, where we also included solid. So here we have the saturated liquid line, here and here, saturated vapor, saturated solid, And then this line's important, the triple line. Why is it important? It's because this is where the solid, liquid, and vapor phases all coexist in equilibrium. So next, I'm just going to show you the pressure versus temperature diagram. So it's pretty straightforward. We see solid, liquid, and vapor. Nothing really interesting here, except here we have triple point, which is essentially the same thing as triple line. So it's the temperature and pressure at which solid, liquid, and vapor phases of the substance coexist in equilibrium. So lastly, if we can combine all these three properties, we get this diagram in 3D. It's pretty cool. Not much to say. Okay, so that's all. Thank you for listening. I hope that was helpful. Have a great day. Goodbye.